All right, sorry, I'm trying to record for Kaylee. Hi, Kaylee. All right, so 2.3 notes. We are looking at the leading coefficient test. So leading coefficient, going to the other side of this page. It's what you were looking at already when it asked you for like degree on a few problems in the homework. So what's the degree of the polynomial, and then what's the coefficient? So when we're talking about degree, the leading coefficient test, it's implied, leading, hopefully it feels like kind of common sense to you, that we're looking for the highest exponent on our variable, and then we're also going to consider the sign of that coefficient. When I say sign, I'm talking positive or negative. So there are two things really four things we're going to look at, but two categories. I want to consider whether my leading term is even or odd based on its exponent, the degree, the highest power that I see for that function, and whether its leading coefficient is positive or negative. So I want to think even or odd in the degree, and coefficients are those positive or negative, because that's going to give me some information depending on how I classify. So the leading coefficient test, when n is even, so n, I want to just specify, I'm talking about exponent. Okay, so when I say n is even, I mean that the exponent is even. So when n is even, we're going to have even over here, and we'll do odd on the left side. So n is even if leading coefficient, bless you, and we're going to start abbreviating coefficient here, but if leading coefficient is positive, the graph rises on both ends. And so how we're going to note that, we're not going to complicate this, up, up. Okay, so on the left and on the right hand side of that graph, my curves are, my end behavior is one way to describe it. I'm rising on both sides. What's an example of a polynomial that has an even exponent that you're very familiar with? X squared, right? So think about x squared. When x squared is positive, so what is your graph doing on its ends? So on the left side and on the right side, I am going up and up. So whenever I have a positive coefficient and my exponent is even, now the cool thing about this is that it works out no matter how many terms you have. So if it's an even, so we know x squared, and I relate it back to x squared to help us remember it. But if I had x to the 6th plus x to the 5th plus blah, 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 all the way down the line, I'm looking at that first term, and that's going to tell me what I need to know about my end behavior. Now, of course, other stuff will happen, but it's as simple as, is n even or odd, positive or negative? So thinking about, what do you do to flip the graph over? Because this is our y equals x squared, right? So if I want to have a negative coefficient, so y equals negative x squared, what's going to be different? He's going to flip across, we'd say x. Good. So as an example for this one, we'll say if leading coefficient is negative, graph falls on both ends. And to note that, we'll just have downward arrows. So on the left and the right hand side of my graph, I'm going to see down and down. So parabola, I always think about a parabola. If positive x squared opens up, so up and up on the ends, negative down and down. Any questions yet? All right, so then we come over here, and when n is odd. So if leading coefficient is positive, graph. I want you to think about an odd-powered function and what that looks like. What's one you're familiar with? Cubed. So y equals x cubed. Looks roughly like that. So how would we describe? So instead of it rises or falls on both ends, I'm going to say that the graph falls on the left, rises on the right. And as far as arrow notation, on the left side, my graph is going down, but on the right side, my graph will be going up. So down and then up. Any questions about that notation? I don't want to confuse anybody. I feel like hopefully, if you don't overthink it, it's okay, but if you have any questions right now, please ask. So then, my other combo. If leading coefficient is negative, graph. So I'm going to reverse it. The graph will rise. So graph rises on right. Sorry, rises on left. Oh, and I have to make it ugly. I hate it. Okay. Graph rises on left, falls on the right. And so that would be if I made it negative x cubed, and remember that's just a reflection, so a negative x cubed would look like that. And so as far as our arrows go, I would have up followed by down. So the reason I care about this is we're going to be trying to sketch some of these polynomials by hand. Now we don't need to get a perfect sketch. It won't be exact. We're not going to hit like every single ordered pair that function actually passes through. But we can get a surprisingly good idea of what that graph's going to look like just by using our leading coefficient test and knowing what that end behavior is going to look like. Now a couple of other things that we're going to use to help us create our sketches would be the zeros of our polynomials. So the function f has at most n real zeros. So this is an important thing to consider. What does n represent again? Exponent. So whatever the power of my exponent is, that's the maximum amount of real zeros that I can have. So if I've got a power of 3 and I ask you, hey, true or false, x cubed can have 4 zeros. You better say false because you're looking at that exponent and you see that you have a power of 3, so it would be impossible to have 4 real zeros. So at most, n real zeros based on exponent. So best case scenario. Sometimes you might have a power of 5 and you have no real zeros, and it might just not intersect, the x-axis. So you'll see that happen too, but at most, n real. The graph of f has, again, at most, it doesn't have to have this many, but it has at most n minus 1 turning points. And these are points where the graph changes from increasing to decreasing or vice versa. What's that called where you have a turning point and your graph changes from increasing to decreasing? It's a fancy word we learned for it at the beginning of the year. I love it. Extrema.
Extrema.
Extrema. All right, so absolute or local turning points, that's what extrema points are. They're turning points. We have changes from increasing to decreasing. Now, again, look at how much stuff the exponent tells us. Exponent tells us a lot. It gives us some insight into our end behavior. It tells us how many zeros are possible, and it also allows us to know how many turning points I can have. So note that I cannot have as many turning points as my exponent. And think about x squared. You've never seen a parabola that had 2 turning points, right? We only have 1 turning point from decreasing to increasing, and that's because at most I have n minus 1 turning points. So just kind of keep that in mind as you go forward. That's one of the only ways when you're sketching these you can kind of make a mistake, is if you get too many turning points based on what that exponent was. So we can't go crazy with turning points with a small exponent. So we're going to start with finding the x-intercepts of this graph. So find the x-intercepts of f of x equals, we're going to do this algebraically. So x-intercepts, what is x when y is 0? When you have 4 terms and you need to factor, what type of factoring are you going to perform? It has a name. We call this factoring by something. Grouping. Factoring by grouping. Exactly. So to factor by grouping, those of you are like the memories are flooding back to me, the bad memories. All right. To factor by grouping, it's kind of like the name implies, it's like we group the first 2 terms and the last 2 terms. We're only doing this when we have 4 terms. Okay, so 4 terms, factor by grouping. To factor by grouping, I'm going to factor out the greatest common factor from my first 2 terms. What's that going to be in this case? X squared. Very good. So x squared. When you factor something out, there's going to be something left over. So I factored out the greatest common factor, and now I'm going to write my parentheses with what remains.
Wouldn't the greatest common factor just be x?
X squared.
Greatest common factor, so how many, so you want to think about the quantity, the power of the x's that you have in common, because we're only looking at the first 2 terms for factoring by grouping. So you're right, if I go down the line, then I have that x, and then really if I add the 1 into it, I can't even factor out an x at all. But for this technique, I'm looking at the first 2, and I want the highest power on x that they both share, so it would be x squared. So I'm going to have x minus 1 remaining when I factor out x squared. I'm going to follow this up with factoring out a negative 1. Now, why a negative 1? So it changes the sign, but why do I care about that? These need to be the same. Good. So y'all remember that. That's fantastic. To factor by grouping, our sets of parentheses need to be a match. They cannot be different. Okay, so I can't have x minus 1 here and x plus 1 there. They have to be identical factors with each other here. Now, what you factor out. So if you've done all this work, be careful to not make this last mistake here. What you factored out, those 2 items come together to create one factor. So x squared and the minus 1, the greatest common factors will come together to create the factor x squared minus 1. This factor, this x minus 1, only exists one time. Do not write it twice. We see it twice because we found that common balance between the first half of our equation and the second half of our equation. But the factor itself doesn't actually exist twice. If you put it down twice, think about if you multiplied it out. Your power at the beginning is x cubed. If you have an x squared and x, and then another x, if you did multiply all of those together, you get x to the 4th, and we don't want that. That should feel like a mistake. So we should see that I would have x to the 3rd if I multiplied it back out. Now this can be factored again. I'm going to factor this one more time. This is a difference of squares. So this will factor to x minus 1, x plus 1, and then I have another x minus 1. So now your roots or your zeros or your x-intercepts. When you set your factors equal to 0, you're going to get 1 and negative 1. I'm going to note underneath this one that you have a multiplicity of 2 for your x equals 1. And your x equals -1, you have a multiplicity of 1. What do you infer that means? The number of times that was a factor, right? So the number of times that I would get this as a solution. Because notice we get x minus 1 and x minus 1 twice. So when I solve that, I get x equals 1 both times. I would say that that has a multiplicity of 2 and this has a multiplicity of 1. Something else that you'll hear from time to time, multiplicity of 2 can also be referred to as a double root. So our roots, because we were asked to find the x-intercepts, so those are your actual answers. But when I ask you about multiplicity, the reason we care about double root, a double root, versus something with a multiplicity of 1, we go back to this kind of even-odd business. Odd multiplicity means graph crosses x-axis. Even multiplicity means graph touches but does not cross x-axis. And we'll see this in a second as far as the difference. So you're going to be asked about multiplicity. Multiplicity is just the number of times that a root occurs. So if you get an answer, a specific answer more than once, if x equals 1 is a solution multiple times, then it has a multiplicity of however many times it was a solution. Even multiplicity is kind of a weird case. It actually does, you're not going to see your graph cross the axis if you have a double root. If you have a multiplicity of anything odd, so 1, 3, 5, 7, your graph will cross the x-axis. So that's going to help us when we go to sketch our graph, which is the last thing we're going to do right now. So we're going to rough sketch this using what we know. You know roots. So I know that at -1 and at +1, my graph will touch or cross the x-axis. Let's think about some things that we know before we create our graph. What is the end behavior of this graph? So using our leading coefficient test. So I have positive odd. So positive odd falls on the left and rises on the right. So this will be my end behavior. So I'm going to fall on the left and rise on the right. How many turning points can I have? How many extrema points can I have? At most. At most, n minus 1. So at most, 2 turning points or extrema points. So I'm going to wait for a second and let you ask if you have any questions with anything we've written down yet before we create our graph. What I would like for you to do when you create your graph, if you know it falls on the left and rises on the right, this is what a lot of times, just to kind of differentiate, so there's some uncertainty in here. We don't exactly know for sure what the graph's doing, but I do know that I am falling on the left and I'm rising on the right. And so we'll put that kind of in a solid. A lot of times you'll see that in the book too. Like that will be drawn in solid lines because that's not like a tentative thing. Like I know for sure that that's happening. And then what you'll see a lot of from there will be dashed lines. So when I approach -1, because it has a multiplicity of 1 and it's odd, that means I pass through this point and I cross the axis here. So I'm going to pass through this point and I'm going to cross the axis. Now, I'm going to have some turning points. Where those happen, that's kind of up to you. So this part, we're going to dash it, or it's not set in stone. But I know that whatever I'm doing in here, my graph is going to have to hit this point. But here's what's weird. It touches but doesn't cross. So I'm going to touch it, but I'm not going to intersect it and pass through it. So my graph's going to touch it, the point exists, and then I'm going to move on with my life. And then you check and see, does this seem reasonable? So what we just created, it hit the zeros we wanted it to. We considered the multiplicity. I know that for x equals 1, it's a double root, so it shouldn't pass through. But with -1, I'm going to pass through. I know because it's positive and odd that I'm going to fall on the left and rise on the right. And I know that I can only have 3 zeros at most. I'm not breaking that right here. I've got 2, but it's at most, so that's okay because one of them was a double root. So I understand why I'm not seeing 3. From there, turning points. You want to consider, do I have too many turning points? If you don't have enough, that's not necessarily a bad thing. You don't have to have the maximum amount of turning points in every problem, but you can't have more. So I know I can only have 2 turning points, so I shouldn't see 3 extrema points. So if we were talking extrema, we could call this a turning point. So that's a turning point, and this would be a local max. Okay, so that's going to be a local max if you had to get specific with it as far as extrema goes. It's not the absolute highest y value ever, but in that region I had a change from increasing to decreasing, and so I do have a maximum here. Over here I have another turning point at my 0. So I have another turning point. And this guy is going to be called a local or relative minimum because I'm changing from decreasing to increasing. So in this region of the graph, this is my lowest point. So I'd consider that a minimum. Questions? All right. What I want you to try to do for the last little bit of class here, I'm not going to ask you to graph these yet, but I want you to give me end behavior, number of roots, and number of turning points.
So we don't have to graph it.
You don't have to graph it. And so when I say number, I mean max. So what's your maximum? Maybe if you actually graph it, you would see like, oh, this one could have had 3 turning points, but it only has 2. Okay, so you don't have to actually graph it, but I want you to use the information that we just talked about to go through this page. And as far as end behavior, just use the arrow notation. You don't have to write that it rises and falls and all of that, but use the arrow notation. Think about how many roots you could have and think about how many turning points you could have and do that for these 7. And when you finish that, you're done for today.
Which one's the root?